Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss a variation of conductivity and molar conductivity with concentration. Last class I have discussed that a strong electrolysis. In case of a strong electrolysis, what will be the conductivity and molar conductivity? I have discussed how conductivity and molar conductivity will change with concentration. Then in case of a strong electrolyte, I have discussed. Now I am going to discuss in case of weak electrolyte. But before coming to the weak electrolyte, I want to tell about the Kohlrausch's law. That Kohlrausch's law, actually, this scientist name is Kohlrausch, Kohlrauschh, Kohlrausch. Again I am telling you, Kohlrauschh, Kohlrausch. Then Kohlrausch has given one law that is called Kohlrausch's law. Then this scientist, what he did, I am telling you. Kohlrausch examined these things, molar conductivity at infinite dilution, or he has examined value of this molar conductivity, means lambda m at infinite dilution, that is the limiting molar conductivity. That value he examined. When concentration was 0, that time what was this value? Lambda m, that is the molar conductivity. He examined that value. Okay. And he has examined for a number of strong electrolytes and observed. What he observed? He observed certain regularities. What was that? He noted that the difference in standard lambda m, that is the molar conductivity at infinite dilution of the electrolytes like sodium NaX, you can tell NaX and Kx. For any x is nearly constant. He studied like this, that NaX value, electrolytes, he studied particularly for NaX, Kx, that value he studied. Then he found that the difference in molar activity at 0 concentration or molar activity at infinite dilution or limiting molar activity value, what he found, that difference in molar activity at 0 concentration of the electrolytes NaX and Kx for any x is nearly constant. X is halogen. Fluoride, chloride, bromide, iodide, like that way. NaX means maybe NaCl, maybe NaBr, NaI, and Kx means same way. KCl, KBr, Ki. Then he found the difference between the two NaX and Kx. NaX and Kx value of this lambda m at 0 concentration is constant. Means NaX lambda m at zero concentration of NaX, and again lambda m at zero concentration of Kx is equal to constant. Okay, this he concluded, this he found. Okay, means lambda m 0, you can tell, lambda m 0 means zero concentration of NaX minus lambda m 0 Kx, that is equal to now X. If you suppose X is chloride, now you are considering X is chloride, then NaCl minus KCl, Cl is common, NaCl minus KCl, that is equal to the KCl and NaBr. See here, KCl difference I am talking about, KCl minus NaCl, okay, that is equal to KBr minus NaBr. Then see, K with the KCl is there, KCl, again NaCl, then now it becomes difference between Kx minus NaX, Kx minus NaX. Here X is equal to same, Cl, then that is equal to, its value is equal to now KBr minus NaBr. Again here also K and Na is there, but halogen is different. One side bromide is there, other side also bromide is there. KBr minus NaBr. Okay, K and Na difference is there, but Br is same. That is equal to first one, that is the KCl and NaCl. KCl and NaCl means only there is a change of halogen. In the first case, difference of KCl minus NaCl. Cl is common, K and Na is same. K and Na is different, Cl is common. Then its difference is equal to KBr, NaBr. Both differences of molar conductivity at infinite dilution is same, means constant. That also, now you compared this NaCl and KCl. Second, that was equal to KBr minus NaBr. Now I also you can consider same way, that is equal to now Ki minus Nai. Correct? Same things. Only you are taking these things, K and Na difference, but halogen is whatever type of halogen is there attached with K and N, it is not going to make any change in difference of molar conductivity at infinite dilution. No change. Okay. Then this I have told you that according to Kohlrausch's law, this is the this actually, that is according to Kohlrausch's law, this difference is constant. And its value actually was according to Kohlrausch's law, its value was 23.4 Simon centimeter square per mole. You got a difference of 3 set, I told you, 3 pair I told you, that KCl, actually it is written like that, lambda m you have written upside upside 0 you have written, and down near the actually M you can write KCl in bracket, a small KCl you can write, KCl in a bracket you can write near the M. Okay, this is the rule to write, means lambda M and near only KCl, means lambda M of KCl, and before the this above the lambda you write 0, like that way. KCl written, NaCl same way, lambda M down near that, near the M you write now NaCl, NaCl means lambda M at 0 concentration of NaCl, correct. Then this is the actually way how to write this differences. Then this differences in case of chloride, bromide and iodide, it was found to be equal, and its value was how much? Then its value was 23.4 Simon centimeter square per mole. And now we have X was whatever value of X was there, that I have told you. In case of potassium and sodium I told you. Now one more things he observed, that lambda M NaBr, sodium bromide, minus NaCl. Now both ions are same. Sodium now they are. In the beginning you have seen potassium and sodium differences. Now here that cation is same, sodium, and one is sodium bromide, other is sodium chloride. Means one time X is equal to bromide, other time X is equal to chloride, but cation is same now. In the beginning you have seen that one cation was different. One was potassium, other was sodium, correct? And X was common in that time. Now reverse case, cation is same, halogen is different. Then in that case also he observed that it is a constant. Means now another set, if you will compare sodium bromide minus sodium chloride, that is equal to potassium bromide minus potassium chloride, correct? Now cation was same, halogen was different, like NaBr minus NaCl, Na common, that is equal to now potassium bromide minus potassium chloride. That both set I told you difference between these are again equal. When cation is same and ion is changing, anion is changing, correct? Means sodium bromide minus sodium chloride, sodium same, and halogen is changing, bromide and chloride. Then its value difference is equal to, if you will consider potassium, another cation, potassium bromide minus potassium chloride. That time also difference was found to be same, constant, and in this case value was 1.8 Simon centimeter square per mole, correct? This he observed in his experiment. Okay. On the basis of this observation, he concluded, or you can tell, he enunciated Kohlrausch's law of independent migration of ions. This is called actually Kohlrausch's law of independent migration of ions independent. Okay. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual. This again I am telling you, limiting molar conductivity of an electrolyte can be represented as the sum of the individual contribution of the anion and cation of the electrolyte. Very simple way. What is actually this contribution in NaCl? Contribution due to Na means conductivity of sodium ion plus conductivity of chloride ion. That is the total. You make it total sum. That is the molar conductivity of NaCl. Sum of two ion, cation and anion. Correct? This he has concluded. He has enunciated the law that molar conductivity at zero concentration is equal to the sum of molar activities of cation and anion. Very simple way. Correct? And this is actually called limiting molar conductivity. Okay. At infinite dilution, in that situation, molar activity you are calculating. Then it is very easy to understand, because you are now considering at zero concentration. And that time whatever possibilities was there for both ion, cation and anion, just it moved. Now there is no scope. At zero concentration got full freedom. Hence it is the sum of cation and anion. Okay. Then Kohlrausch's law, this actually is called Kohlrausch's law. Okay. Then limiting molar conductivity of an electrolyte may be NaCl, KCl, MgCl2, Na2SO4, anything can be represented as the sum of individual contribution of the anion and cations of electrolyte. Now, if lambda m ion, I am actually for this thing, for ion molar you can say limiting molar activity is represented by, that is also its symbol is just like reverse of y. Y you are writing, that is also called lambda only. Then it is just like a y. It is only for ion, just reverse of y. Same way, like that way you can write y for cation plus y for anion. Y for cation plus y for anion means limiting molar activities of cation and anion. Okay. For lambda just like reverse of v, you were writing for mole, that is for electrolyte you were writing, for electrolyte. But here you are writing for ion. Here you are writing for ion. Okay, that is cation and anion. This is the difference. Then here it is represented like lambda, it is called lambda, but it is just like a y, reverse of y. Okay, in the same way you can write lambda just like a y, reverse of y, m, and there in bracket you write suppose sodium ion, the Na plus, in bracket write Na plus Cl, then again lambda m, in bracket you write Cl minus, and 0 0 you have to write upside. Here also for this salt, what you are writing NaCl, KCl, then 0, what you are writing the same way, only just here lambda you are representing y, just reverse of y, all representations same. you write 0 upside and down M, and just near the M you write cation and anion, and in the middle you write plus means cation lambda M cation plus lambda M anion at 0 concentration. Okay, then this is the actually main law, that is the for salt you are writing. For salt you are writing here that for salt like NaCl means molar conductivity at infinite dilution of NaCl, as for example, is equal to cation and anion. Ionic conductivity means conductivity of cation plus conductivity of anion at infinite dilution. Simple way. Correct? For NaCl is here NaCl. Then now its value, direct NaCl value, conductivity of NaCl value at infinite dilution is equal to now sum of the ions. Sum of the ions of sodium and chloride. Okay, then this is actually law, means both side at equilibrium. Both side at equilibrium, not distant. Both side at infinite dilution. Both you are considering at infinite dilution, means 0 0 you have to write in our passage. Okay. Then this actually is actually called limiting molar conductivity of this Kohlrausch'S law. Kohlrausch'S law is called Kohlrausch'S law of independent migration of ions. You are using ions, sum of the ions, simple way. In general way, how will you tell? In general, if an electrolyte on dissociation gives suppose some number, cation will give 2 number, in 3 number, just like you can say Na2SO4. Then Na2SO4 when it will dissolve in water, it will give 2 sodium ion, 2 Na plus plus 1 sulfate ion, SO4 2 minus, total 3. 2 sodium, 1 sulfate, total 3 ion it will give. Correct? Then if suppose this is the case, NaCl give 1 Na, 1 Cl, 1 sodium ion, 1 chloride ion. If in some salts are giving 2 cation and 1 anion, as for example Na2SO4, sometimes CaCl2, 1 cation and 2 anion. Then in that case, in a general way, how will you tell about the limiting molar activity? Then limiting molar activity is equal to, now this coefficient you have to write before the ion, before the cation you have to write some this things, coefficient like new sign you can give. Okay, suppose cation is giving 3 and anion is also giving 3. Then how will you write? Then just like a nu, a small b like that is called a nu. Okay. Then nu you have to write, and suppose for the cation has positive signs, then here you should write a small b and plus sign. Means this is the coefficient of cation, B plus. Same way for the anion you will write B minus, B small b minus before anion. Correct? Before cation B plus and before anion B minus. Okay. Then you can write in general way that lambda m at infinite dilution is equal to V1 V plus lambda means for ion conductivity, cation conductivity at infinite dilution plus anion V minus, then anion conductivity at infinite dilution. Just simply same way, cation and anion you have to add, means plus. Only difference is that now that coefficient you have to write, coefficient of cation, coefficient of anion, that is represented by nu plus for cation and for anion nu minus. Okay, then this is the actually in general way Kohlrausch's law is written like this way. Okay, means lambda m at infinite dilution is equal to nu plus lambda you can say cation. Lambda cation means also you can write lambda plus term is for cation, nu plus lambda plus also you can write. Okay, nu plus lambda plus, like that way nu minus lambda minus, and 0 0 you have to write for all three terms, for lambda m also and for ions also. This is called Kohlrausch's law. Kohlrausch's law of independent migration of ions, means sum of the ions, conductivity of cation and anion, just to add how many cations plus how many anion, that you just add both with coefficient. With coefficient you add both cation and anion, add and make it sum. What is the total? That is for the salt. As for example, this lambda m NaCl. Then here you will write NaCl means V plus, that is equal to 1, Na plus. Again for negative also 1 into lambda for anion means Cl. Then if a value is given for sodium and chloride ion, then just to add it, ionic these things, conductivity you are knowing, then molar you can calculate very easily. Just to add both you add, you will get the molar. Then molar conductivity is equal to total sum of the ionic activities. You have to consider coefficient also, you have to multiply. Suppose 2 cation was there, then 2 into cation, plus 3 anion was there, then 3 into anion, add it. That's enough. That you will get molar conductivity, limiting molar conductivity. Okay, this is the very useful in numericals. This concept is used actually. Then what I told you, if value you are knowing, then easily you can calculate the molar conductivity. Here one thing I want to tell you, that sometimes which you can't know, weak electrolyte. Now I am coming for these things, weak electrolyte. Then weak electrolyte, it will not dissociate fully. Name itself is a weak electrolyte, means it will not dissociate like a strong electrolyte. It will dissociate very less in comparison to the strong electrolyte. Suppose a strong electrolyte is dissociating 99%, then weak electrolyte will dissociate 70%, 75%, 80%. What type of electrolyte is there? According to that. That's why it is called a weak electrolyte. Dissociation is very less. Then now if you want to know the molar activity of a weak electrolyte, molar activity of a weak electrolyte, then how will you come to know? How will you come to know this molar activity of weak electrolyte? Then you can know with the help of Kohlrausch's law. Kohlrausch's law. Okay. By use of the Kohlrausch's law, because in Kohlrausch's law, they will give the value of ions, only for ions. As for example, acetic acid you don't know. Acetic acid, suppose you don't know molar conductivity of acetic acid, you don't know. But you want to calculate. Then how will you calculate? Then for that, you want acetic acid. Molar conductivity of acetic acid means CH3 COOH, means acetate ion and H ion. You require acetate ion and H ion. Then they will not give direct acetate ion and H ion. They will not give direct value of acetate ion and H ion. They will give value in indirect way. Means, as for example, they will give value for sodium acetate. In question, it will be given sodium acetate. Then in that sodium acetate, acetate ion plus sodium ion will come. Then sodium acetate, that acetate value they can give. Sodium acetate value they will give. Okay, sodium acetate value. After that, because you want HCl, then they will give, you want H ion. For acetate ion you want CH3 COO and H plus. Then direct value will be not given. Indirect value will be given. Then sodium acetate value they will give. And HCl value they will give, not direct H. HCl value they will give. And NaCl value they will give. NaCl. Then see, your what you want, you are not getting in a direct way. They are giving sodium acetate. Sodium acetate they will give. HCl they will give. NaCl they will give. Then how will you get acetic acid with the help of these three? Then now you know the sodium acetate will ionize. Sodium acetate will ionize like CH3COO plus Na. Sodium acetate. HCl will ionize H plus Cl minus. Correct? NaCl will ionize as Na plus Cl minus. If you write in equation form, then what you will find? That Cl minus, because you want acetic acid, CH3COOH. Hence you have to adjust like that. Sign you have to adjust. Plus or minus sign of the salt you have to adjust, so that all should cancel and what you want, only that should remain. As for example, sodium acetate was there, then CH3COO minus plus H plus. Correct? This is sodium acetate, H plus. But Na plus, sodium acetate, Na plus, CH3COO minus plus Na plus. This Na plus you don't want. Then now NaCl is given. Then there you write minus NaCl. Then minus NaCl will write. Then this both Na will come plus Na plus. Sodium ion plus sodium ion minus sodium ion. Both will be cancelled. Then what will be remaining? Then acetate ion will be remaining. And now chloride ion is remaining. Then again you don't want chloride ion. You want H ion. Then now HCl is given. Then minus HCl you write. Okay. Minus this you have to write. Then what will happen? Actually all things you write in a bracket. Then HCl you will write. Then you will get H plus Cl minus. Then Cl, what was, they both will cancelled. Only hydrogen will remain. Hydrogen will remain. Then now, what you wanted, only that is remaining. But they have not given direct value of sodium acetate ion, not given direct value of H ion, they have not given. They have given sodium acetate value, they have given HCl value, they have given NaCl value. But you can write ionic wise. Ionic wise you can arrange what you want. You arrange such type of, in such way you arrange by keeping proper sign, minus and plus, as per your requirement, so that you finally only acetate ion and H ion should remain, other should cancel. You have to adjust like that, positive and negative sign. Then in question they will give direct salt value, they will give, not the ion value. Correct? Then like that way, if you write direct salt value, will write, then all are cancelled. Then what will remain? That will be only for acetic acid. Acetic acid. Okay. Then now I am just discussing this main things I told you of weak electrolyte. Now I will go little details. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentration, and hence for such electrolyte the change in lambda m with dilution is due to increase in the degree of dissociation and consequently the number of ions in total volume. In total, it depends upon the number of ions in total volume of solution that contains 1 mole of electrolyte. In such cases, lambda m increases steeply on dilution. Okay, because number of ions will be more with dilution. Then lambda m, this things for acetic acid, lambda m, or you can tell these things, lambda m at infinite dilution cannot be obtained by extrapolation of lambda m to 0 concentration. You will not get. Okay, again you listen these things. Due to this increase in the degree of dissociation, if you will dilute it, solution if you are diluting, then number of ions will increase. Number of ions will increase in total volume of solution that contains 1 mole of electrolyte. In the beginning it was less, 1 mole was there, but when it was concentrated, that time all ions were not dissociated. But if you added more water, means it became dilute, then it dissociated. Now number of ions will increase. Okay. Then in such cases, lambda m increases steeply on dilution, because now ions are free. Hence delta m value will increase. And especially near the lower concentration, it will be very high. Ions will be more. Therefore, lambda m at infinite dilution cannot be obtained by extrapolation of lambda m to 0 concentration. At infinite dilution, that is the concentration C becomes to 0, tends to 0. Electrolyte dissociates completely. At that situation, electrolytes dissociate completely means alpha is equal to 1. Alpha dissociation constant, particularly for a strong electrolyte, alpha is equal to 100%, that is the 1. Alpha is equal to 1. Okay. At infinite dilution, concentration C change to 0, electrolyte at 0, and electrolyte dissociates completely, but at such low concentration the conductivity of the solution is so low, but at low concentration the conductivity of the solution is so low that it cannot be measured accurately. At low concentration, conductivity will be very less, hence it can't be measured accurately. Therefore, lambda m at infinite dilution for weak electrolytes is obtained by using Kohlrausch's law of independent migration of ions. Okay. At any concentration C, C is concentration, if suppose alpha is the degree of dissociation, alpha is degree of dissociation, then what will happen? Then then it can be approximated to ratio of molar conductance. Ratio of molar conductance means lambda m at the concentration C. Here simply you can tell alpha will be equal to lambda m divided by lambda alpha. Alpha means here you can tell that is the lambda m at any time at infinite dilution, lambda m at infinite dilution divided by lambda m. Lambda m means that is one is at any concentration, lambda m at any concentration, and other is at infinite dilution. Then here you can tell alpha is the ratio of molar conductivity at the concentration C divided by limiting molar conductivity, that is the lambda m power 0 you can write. Then here alpha means degree of dissociation, that is equal to lambda m divided by lambda m at infinite dilution. Means at any concentration C value will be different, but lambda m value at infinite concentration, that time value will be different. Both values are different. Then their ratio is called alpha. Their ratio is called degree of dissociation alpha. Now actually simply you are comparing that any concentration other than at infinite dilution. Correct? Their ratio you have to obtain. Correct? Lambda m at any concentration divided by lambda m at infinite dilution. Their ratio. Just like out of 100 you got 60 marks, then 60 by 100, full marks was 100. Same situation is there. Then now further you know that K value or K alpha dissociation is a degree of dissociation. Alpha is the degree of dissociation. Now you know dissociation constant. Dissociation constant already I have discussed K, that is called K. Okay. That for a weak electrolyte like acetic acid CH3 COOH, for this Ka you can write a small a. A small a means acetic acid. You are talking about the acid Ka. Then for the acetic acid you know that C alpha square divided by 1 minus alpha. Here, because acetic acid will dissociate into the state ion plus H ion. State ion plus H ion means acetic acid, it will when it will dissociate, then you know that because it is a weak acid, it will not dissociate fully. Then suppose 1 mole you have taken, then only alpha mole will decrease. 1 minus alpha will remain undissociated. Then alpha, it will give alpha mole, it will give H ion, alpha mole it will give acetate ion. Both alpha mole it will give, and 1 minus alpha mole will be remaining. Simple, out of 100 only 75 mole dissociated, then 25 mole will be remaining. 100 minus 75, like that way 1 minus alpha is remaining, and alpha state ion and alpha H ion it will give in equal number, correct? Then now if we suppose their concentration is C mole per liter is there, then you multiply C everywhere, then C into 1 minus alpha will remain at equilibrium, and C alpha of state ion you will get, C alpha of hydrogen ion you will get. Okay, that's why 2 times you will write C alpha into C alpha, product divided by concentration. Then product is C alpha into C alpha, and reactant is 1 minus alpha into C. Then 1C, upright and down it will cancel. Then it will remain C alpha square divided by 1 minus alpha. Then this is the Ka value. Then now C alpha square divided by 1 minus alpha. But now you know value of alpha. Just now he discussed you alpha is equal to lambda m divided by lambda m at standard, lambda m at infinite dilution. That ratio means lambda m divided by lambda m 0. Then in the place of alpha, this you write. In the place of alpha you write lambda m divided by lambda m 0. Then you will get C, finally you will get C lambda m square divided by lambda m 0, lambda, and in bracket you will get lambda m 0 minus lambda m. Nothing. You have to simply put the value and simplify it. You will get C lambda m 0 divided by lambda m, only lambda m 0, and down I am talking about, down it will be in denominator lambda m 0, and in bracket lambda m 0 minus lambda m. This is the relation. Okay. Then I have discussed now these things, Kohlrausch's law, and it's actually it has many application. Numericals are there. Then I will discuss it in the next class, and only this 2 formula what I told you, alpha value and this alpha value kept in the K value, means dissociation constant expression. In that you have put the value. Then all numericals will be based on these 2 formula, and Kohlrausch's law what I discussed, that you have to use. Okay. Then other applications are there and numericals are there, that I will discuss in the next class. Thank you.